This is the second part of the handouts which I put on the website. By the way, when I made those handouts and I said it's for the week one, I miscalculated a little bit. So those handouts are there too large for the week one. So I mean, like we only get through parts for the only portion of the part two of the handouts. Some of it will go to the next week. Just because of my miscalculation, I just made it too big for this week. So anyway, as I promised, we're going to discuss with you limits now from the more professional, more mathematical point of view. Hopefully, it will take us 2 lectures to get some ideas, fundamental ideas about the limits in n-dimensional space, as opposed to the limits of numerical sequences as you know them. And this discussion normally starts with the concept of metric. And that's what it is. So metric, it's a function of 2 variables. Each of them individually is an n-dimensional vector by itself. You see, that's what it said here, right here. Delta, it's a function which takes 2 arguments. Each of them by itself is an n-dimensional vector. It returns a number. And we normally require a few properties from such function. Well, first one is that this value, the value of my function, it never goes negative. It's either 0 or above 0. And there's a name for this part of the metric properties. We call it positive definite. Well, to be precise, actually, positive definite means not only that the metric is non-zero, but also the second condition that the metric is 0 only if and only if when both arguments are identical, x equal y. A second one called the symmetricity of the metric. If you change the arguments around, the metric delivers the same value. And the last one is called the triangle inequality. And that's demonstrated by this diagram. I mean, even though I use the distance to demonstrate the metric, in general, metric may be any other function subject to triangle inequality. And I'll show you some examples on the next slide. If you saw the handout, you saw the examples of other metrics different from the conventional Euclidean distance, which also subject to triangle inequality. So that's how you formally write this triangle inequality. Distance from x to z doesn't exceed the combined distance from x to y and from y to z for any triple combination of x, y, and z. Any function which is subject to these 3 conditions, we call it a metric. In this course, you won't see many of those. I'll give you just, well, it's a 3 examples, but actually one of them gives you the whole family of examples. There are other versions of metrics, but these 3, they are basically so ubiquitous across many parts of analysis. You will see them if you continue your mathematical study later on with the other topics. You'll see these metrics there too. So here's the example. Well, first example is the Euclidean distance. It's a distance you know very well. And in this topic, we will fix the specific notation for this, a very concrete notation for this metric. I'm going to use the letter D for such metric. This one, letter G. The other example, which I call P distance, it's looks like a Euclidean distance, but you see, this time I take the sum of the p power rather than the second power, and I take the pth root rather than the square root. And p here goes maybe any number from 1 and on. When p is 2, obviously this one becomes the Euclidean distance, or metric, sorry. It is not a trivial, actually, it's not a trivial exercise to convince everyone that this is a metric, meaning that this one satisfies these 3 requirements. Positive definite, symmetricity, and triangle inequality. First 2 is easy. I mean, positive definite and symmetricity, they are just sitting on the surface. If you look at the formula, it's almost there. But triangle inequality, it's quite an effort to establish that. We're not going to do that. One of the later topics, probably if you take any of the higher or next mathematical topics here, you will probably see that. At this stage, you have to believe me that if you take G sub P, that will be a metric. It will be subject to triangle inequality. And there's an infinity version of the P distance, which I call infinity distance. And that's another notation we're going to fix for that. It's a max of individual distances or differences of components. See? And that's the short way to write that. Yeah, so these are 3 examples, 3 fundamental examples of metrics. You will meet them, like I said, in many other topics. We're going to briefly look into them. And the first thing I'd like to discuss with you in relation to this matrix that is what is called the equivalence theorem. As a matter of fact, one of you yesterday came to me and sort of preempt this equivalence theorem. And now, I mean, like it was you, what's your name? Mary came to me and she asked, can I just explain a piece of a proof she was reading? And actually, in the part of that proof, it was exactly the equivalence theorem we're discussing right now. So you just came one day earlier with that question. Right, so the theorem which we need to know, and that's a very helpful theorem when you just think about this matrix is this. Well, basically that's the theorem. It says the P metric is always, when we have a relation like this between two metrics, here we'll have two metrics, d infinity and dp. When we have such a relation between two metrics, so one is controlled by the other and the other controlled by the first one, in return, maybe with a different constant. You see here's a constant, n root p. If you have such a relation, we call two metrics like that equivalent. There is a tutorial question. I mean, I'm working right now on tutorial questions. Right, before I come here, I was putting the questions together. One of the questions which I will publish tomorrow will be exactly about the equivalence of metrics. So that's the example of the equivalent metrics. So it's the first part of the theorem. Second one, which basically follows from the first one, that's why I call it the corollary of part one, is that not only infinity and p metrics have some relations, but p and q metrics also have relation like this. And there's a third part, which is a significant improvement of number two. It's the relation between p and q metrics, but with a different constant. Look at this. The constant here is n root r, where r number computed in this very interesting way. The first two parts, they're relatively easy to prove. The argument we discussed with Mehdi yesterday, it's almost identically repeats itself, and I'm going to show it now to everyone. The third part, it's quite challenging. I don't know if anyone will be able to establish this one, basing on the first two. We're not going to do it in class. It's a famous inequality, as a matter of fact. Those of you who will later will study these DP metrics with more details, you'll probably see the proof for the third part. But it's a lot harder to prove than the first two, but we're going to look at the first two only. For this topic, first two parts of this theorem are sufficient. The third one I just introduced, well, because I like metrics and like relations between the metrics, so I just, yeah. All right, so I have a proof for the first two parts. Here it is. Matrix equivalence theorem, that's what we have to open. Okay, I just rearranged the zoom a little bit, so this time it should be better. I mean, I readjusted for this resolution of these projectors and everything. So here's the theorem. It's the same theorem as before. I just opened the statement. Look at this. We have two vectors given by components, x and y. Components respectively x1, x2, xn, y1, y2, yn. DP metric, that's how we define it. It's just a repetition of a definition. It's a shorter version. That's the expanded version of the sigma symbol. Basically, it's the same thing. It's just two different ways to write it. It's a condensed one, more advanced one. This is more self-explanatory one. D infinity metric, that's the definition of it. So here's my theorem. The theorem was like this. That's how the theorem was, the first part of the theorem. We have such a double relation between the metrics D infinity and dp, and we're going to establish that. So proof of, well, I call this part A, I call this part B. So A part, first inequality, which we need to prove. Listen to this. Well, first I'm going to take this expression which represents the dp metric. Here it is, the whole expression. Just repeat it here. And what I'm going to do is this. Okay. I'm going to vanish every term in this representation except for the first one. Just my desire to do so. If I do so, obviously because I'm removing the positive terms from the expression will go smaller, right? Obviously. So if I do that, I put this inequality sign, So my original expression greater or equal. First one I keep. All of the others is just 0. And obviously, if you do the arithmetic, it's just the first one with no powers or no roots. So from here, what I can say that my DEP metric for 2 points, x and y, it is always greater or equal than the difference between the first two components. Or greater or equal than the difference of first components, I should say. Well, basically nothing stops me from vanishing every component except the second one, and concluding the similar statement for the difference of second components, and then difference of third components, and all of the other components, right? So basically I can say that, repeating the argument, similarly, I can say that dp metric of x and y is greater or equal than the difference of any other I component, where I takes any value 1, 2, and n. So from here, I can say now if my dp metric greater or equal than every individual difference, obviously it will be equal than the max of those differences. If it's bigger than every individual number, it's bigger than the max of those numbers, right? But the max of those numbers, it's the d infinity metric. And that finishes the proof of this inequality. So you see, as easy as this. The main trick is just we'll be vanishing some components and just end up with this trivial inequality like that. And that's the end of the proof of part A. Now for the part B, well, maybe still copy, I'll give you a chance to copy it. Now if I want to prove part B, that's exactly what we just discussed with Mehdi yesterday. That's the part B of this proof. Look at this. Well, just to make it a little bit shorter, I just decided to introduce the abbreviation. Let me just abbreviate this number with the d infinity, like this. Then, where's my asterisk, I wonder? Ah, here we go. It says by asterisk, and the asterisk marks this. I can say something like this again. Well, it's an obvious conclusion again, right? Because d infinity is the max of all of these numbers. Obviously, d infinity will be larger than every individual number from where the max is taken. So from that, well, that is true for every I, 1, 2, and n. From that, again, I'm taking the expression for my dp norm, this expression, for dp norm. Here's the expression. And this time, rather than vanishing these individual terms, I will replace them with a larger expression, with the d infinity. If I replace them with a large expression, look what happens. This one is replaced with the d infinity to the power p. Next one is replaced d infinity to the power p. Every one in its turn will get replaced by the d infinity to the power p, which is as a common factor across the whole sum. We can factor it out. We can factor it out, and that's the expression we come up with. Well, actually, yeah. This is repeated n times, that's why we have the n factor, which gives me this expression after simplification. That is exactly the B side, look at this. And that finishes the proof of the theorem. It's a very simple proof. Well, if you have, if you like challenging problems, try to see whether you can modify this proof to make part 3 of the theorem on my main slides. That's a serious challenge. Not representational challenge, it's a serious mathematical challenge. Oh, yeah. But for the part 1 of that theorem, that's how it is. Now, second one I call the corollary because it follows from the first one. Let's just listen to that. Yeah. I need to scroll it up again. So second one, which I call the corollary, which means it's a consequence of the first part, it says that we have the following relation between the P and Q metrics. If you take P and Q, two different P and Qs, like that, then when we have such relation, even though I think there's something is missing here. Yes, something is missing in this representation because maybe not. We'll see. We'll see in a second. Should be fine. Here's a proof for the corollary. I start with the this is very simple corollary, as a matter of fact, because we have the first part. It's relatively easy application of the first part. I take the dq metric. By the first part, I have this relation. It's the B side of the first part. We just proved. And then by the first part again, but now A side of the first part, we have this. We just replace d infinity with dp. And that's all there is to it. Just double application of the first part, B side first, and then A side of my first part of the theorem. Any questions? Okay, if you don't have any questions, let's just move on. So what else I have here? Well, now we can discuss the limits when we have metrics. Now we can discuss limits the way mathematicians discuss it. So first, I'm going to fix this terminology. I'm going to call it I'm going to use the term ball with respect to a particular metric, which I use the symbol delta. In place of delta, we can use any metric which is subject to free conditions. You can think of these three examples we just discussed: Euclidean one, d or d2, dp or d infinity. So a ball with respect to a metric, it will be the set of this type. So it's a ball at the center point A with the radius epsilon. That's the one. Quite expectable definition, especially if you replace delta with the Euclidean metrics. You will end up with the well-known ball. And now the definition for the limit sounds like this. For every sequence points in Rn, the limit, so for every sequence xi, x will be a limit if you have this epsilon delta definition, which says for every epsilon bigger than 0, there is an integer n such that past that integer, such that for every index little n larger than this capital N, your x will be close to xn, will be as close as epsilon to xn. Or you can replace this claim by just saying that xn falls within the epsilon ball centered at the point x. Yeah, with respect to the delta metric. Notation-wise, that's what we write. We write either limit of xn equal x, or if we would like to specify the metric with respect to which limit is computed, we put this delta dash in front, just to make it explicit which metric we use to define it. Because if you look at this definition, it's heavily dependent on the metric we use to define our ball, or define our closeness here. So changing the metric means you're changing the definition of the limit. So in principle, limit may change. Yeah. Even though in this topic it's not going to happen, and you will see a reason why just in a few slides from now. Yeah, but in that's a very general, very modern look at the limits in n-dimensional spaces with the help of metrics. Well, I have this example file somewhere. Yeah. What was the name of that file again? Sequence limit example. Here it is. Here's a very typical example. If I have a sequence like this, it's a sequence on a plane of points. If you look closely, you will realize it's just the points which are spiraling into the origin. But it's irrelevant. So I'd like to check that the d limit of this sequence is the origin. d limit of the sequence is the origin, meaning that the Euclidean, the limit with respect to the Euclidean metric of this sequence is the origin. So if I look back at the definition of the limit, I need to compute two metrics, or one metric. I need to compute the distance from my points to the origin in terms of my metric, g. Well, it's a Euclidean metric, that's the computation, right? If I take my components, I compute the way we compute the Euclidean distance to 0 point, to the origin. And if I benefit from the fact that the cos square plus sine square always return 1, it's of course just for the simplicity of the example, I chose such a sequence where the arithmetic is not so hard. You will end up that the distance from the xn point to the origin is exactly 1 on n, 1 on little n, on the index of your sequence. And now you can play with your epsilon and delta. You can say, whichever epsilon positive I fix, doesn't matter how small that epsilon would be, I can always find an index, capital N. And I can even provide the exact formula for the choice of such index, 1 on epsilon, such that after this place, as long as my little n index larger than this place, the distance of x to 0 will never be larger than epsilon. In the proof of the limit from this point, from the definition point of view, the main substance is providing this n. You have to convince everyone that the method of choosing this n for every epsilon works all the time. Well, here, that's my attempt to convince you. No matter how small the epsilon will be, I will always be able to choose an n like that, which will ensure this relation. Yeah. There's one problem, I mean, it's not a problem, but there's one deficiency of checking something by the definition, of course, because when you check that the sequence converges to some limit, by definition, you have to know this value of the limit in advance. Sometimes it may be a problem, but if you know it, then verifying by definition is it's a good way. It's a good, most of the time, it's quite effective way to do things. There will be examples in the tutorial set where you will practice that. Well, that's the same thing. It just this line, this inequality, is just written in the language of balls. So B sub d, meaning that the ball with respect to the metric d, centered at the origin, radius epsilon. Yeah. So that's the sequence which is spiraling into the origin. The whole idea of the limit is that no matter how small you squeeze your ball around the origin, these blue circles, this is the Euclidean balls on two-dimensional place. Euclidean ball is simply a circle, or actually disk, I should be careful, disk. Circle plus the interior of that disk. As a matter of fact, just the interior, because ball is given by the strict inequality, so we don't take the boundary. So no matter how small you take a disk, your sequence eventually will enter the disk and will never leave after that. If you take a disk somewhere else, if you take it large enough, your sequence may be inside the disk for a while, but after a while it will leave. If you make a disk small enough, after a while it will leave and it will never come back. All what I just said in the plain English, it's all encoded in one single this epsilon delta definition. It is a skill which we're trying to teach. Which I'm trying to teach, and you're trying to learn here, how to see this connection between the plain English description and epsilon delta statements. Yeah. All right. Now, that's another result which will help you to test limits with respect to the metric. It's the second theorem. And it says this. If you'd like to check that the sequence converges to something, if you'd like to check something like this, so that the limit of a sequence xn is x with respect to a given metric delta, then rather than checking this, you can check this limit. The advantages is that the limit on the right-hand side, it's a numerical limit. This is a limit of some sequences we just defined. This is a new thing to you, scary thing. The thing we're trying to try to learn how to touch it, how to work with it. Whereas the limit on here, it's a numerical limit. That's a limit from the first year. The one we assume you know relatively well. I think it's a safe assumption, isn't it? Yeah. And a theorem gives you a good instrument, good tool, rather than just checking the limit in terms of the sequences, the way I just did in my example. We can just operate with numbers. Well, if you look at that example, that basically in the whole example, it's already sitting there that we just operated with numbers rather than the sequences. So metrics basically converts limits of sequences into limits of numbers. And here comes the interesting thing. It's another corollary in this result. It says that if you take as a metric this GP or G infinity metrics we introduced today, then limits, as a matter of fact, they're independent of those metrics. So if a sequence converges to some point x with respect to, say, Euclidean metric, you see G for the Euclidean metrics, it will at the same time converge with respect to the P metric. And vice versa. If it converges with respect to the P metric, it will converge with respect to the Euclidean metric. So to some extent, this theorem just kills the fun. Because even though we introduced the metrics, limit-wise, there isn't much difference, between the one metric and the other metric. This is the bad, well, some people say it's a good effect, or you should say it's a good effect, because it was a different, this topic was a lot harder. But this is the influence of the final dimensional spaces, of course. Yeah. Anyway, but I have to convince you into this. I have to convince you about that. I have a proof. It's a relatively simple proof. I'll show you this. Do I show you? Ah, yeah, sorry. Ah, no, this is a typo, obviously. Yeah. This is. I'm sorry. This is a typo. I mean, in my proof, I'll show you the correct. This is a typo, because this doesn't make sense. The prefix GP dash doesn't make sense when you consider numerical sequences. Here is supposed to be this limit with the GP rather than G. This is a typo. Well, I'll fix the typo on my slide. On my dynamic slides, there will be a correct statement. On the left here, on the left, here. Yeah, this is another typo. Yeah, and this is another. Oh, lots of typos. Yes, I'll make a note of this. I'll fix this on the website. Thank you for spelling the typos. That's why I don't like these static slides too much, because you can't fix the typos right on the spot. But on the other hand, lots of material has already been prepared for this course by the other people in the static slides, and I can't really fight this much. I mean, that's why I have to reuse that. I mean, I want to reuse that. It makes my life a little bit easier. But I can't fix typos right on the spot. Well, I took a note. I'll fix the typos later when I get to my office. But let's just look at the proof, and the proof will be correct statement. So. And on the dynamic slides, it's what was the name of the file there? Limit metric equivalence theorem. Yeah, so that's the first part of the same theorem. I just altered the statement a little bit by introducing this new notation, A sub n, you see, just to make it even clearer for you that on the right-hand side, you're looking at the numerical limit. You see, an, it's a number here. It's from the set of real numbers. Yes. Sigma. I don't see sigma. Delta, you mean? Metric. Delta just here stands for any possible metric. So right now we have examples G, GP, or G infinity, but I use the delta symbol to emphasize the fact that the argument and the theorem works for any metric, not specifically D and GP examples. For any metric, the theorem works. And there are some other metrics on top of actually there will be a few metrics in the tutorial questions on the top of GP and G infinity. So the theorem works for any metric, any function which is subject to free conditions. But of course, when we come to the second part of the theorem, we're going to use the first part for the particular choice of a metric, dp and d infinity and d2. Okay? Oh, it's another. Well, this type I can fix on the spot. In this little note, I just say that this is a limit of vector elements. This is a numerical limit, something I already emphasized a few times. Just on the slide, I just repeat that. Let's just see the proof. So it's if and only if, so we have two parts. And I think here, doesn't matter. We go the forward part. So we assume that we have a delta limit of xn equal x. Look what we're going to say from that. Oh, the proof itself, unlike the previous proof, that doesn't represent much of a challenge. It's basically just a proper reformulation of the epsilon delta definition of the limits. So if I just expand this in the way we interpret this, I should say this: for every positive epsilon, there's a place, there's an index, capital N. Actually, I didn't ask you that. Are you happy with these notations? With these notations? Everyone is happy with that? If you don't, this one reads for all. This one reads for all. This one reads exists. For all epsilon positive, for all positive epsilon exists n, such that whenever you take an index after that n, you have this condition satisfied. This is just a literal copy of the definition of the limit for sequences, which I just showed you on my main set of slides. All I have to do now, I have to just alter this expression a little bit so that it looks like the piece in the definition of the limit for sequences. And here's my alteration. Look at this. Because I have this abbreviation for the delta of x and x, I'm going to just replace this delta with the abbreviation. That's what it said here. Next, I will make the observation that because my matrix, it's non-zero function, remember it's a positive definite function, I can change this inequality into this inequality, right? That nothing changes because it's the positive number. And then I can further say this is equivalent to something like this. Yeah, just some trivial modifications. They're all trivial, but now if you look into this last statement, this is exactly a piece of a definition of the numerical sequence in terms of epsilon and delta. If you open your first year book, it says this: limit like this holds if for every positive epsilon there is n such that after that capital N, this one holds. So the only trick in this proof, the only sort of contribution which I made in this proof is this little chain of absolutely trivialities. And they work the other way around, of course, right? If you now take this left-hand side, so I can reverse this. I can take the opposite one now. All I have to say now, if I interpret this the way we interpret limits from the first year stuff, it will be for every positive epsilon, there is an index n, capital N, such that after that, we have this. And then from that, by equivalence, I can include this or this. And that's my limit for the sequences. That's how the opposite side. One of you the other day asked me, can you just say, you can basically reverse every step? That's the place to say it. You can reverse basically in these equivalences. I even wrote the equivalences here. All of them are reversible. Yes?
I was just wondering, why do you need to minus 0? Can't you just do this a n?
You can, but if you check the definition of the limit of a sequence, I don't have a first year book, but we can go Wikipedia. Limit of sequence. Limit of a sequence. Where's my epsilon delta definition? Should be here somewhere. Formal definition. Here, you see? In the formal definition, there must be a difference between the sequence and the limiting point. That's why I put the 0 here, to make it look exactly like that. That's the only point. Because numerically, we can just leave it as an. See what I mean? Where was I? I was here. Any more questions, please? Okie dokie. There was a second part there, right? In theorem. What did I do? I mean, those of you who came from the first year, you know that it's a piece of software which we just wrote ourselves. So this zoom a little bit buggy here. We don't have time so far to fix it. One day we'll fix it. There was a second part in this theorem, right? Yeah, there was a second part which says that, well, with typos. Now you're going to see the second part without typos on my dynamic slides. Look at this. Well, actually, I opened the Wikipedia for nothing because I have here the definition of the limit. I have typed in here. You see, it's another. I didn't realize I have it typed on the slide. So, like I said, I opened the Wikipedia for nothing. That's the same definition, exactly the definition of the limit, and that's how it looks. Okay, let's just look at the corollary. Look what it says. It says that if you compute the d-limit of a sequence, meaning that Euclidean metric, this is the same as if you compute the dp limit of that sequence with respect to the dp metric. Everything is correctly typed now. That's the correct statement of the second part of the theorem on my slides. And that is true for every p. 1, 2, 3, including infinity p. Well, of course, normally you can't write number equal infinity, but I hope you understand what I mean. I mean that if you take the infinity metric in here. I just look at the proof. It's a very simple application of this theorem. Look at this. I take the left-hand side in this equivalence, and I say, by the first part, this is equivalent to, if I restate this in terms of the metric sequence, in terms of this AN sequence, that's how it will be. It's a numerical limit. I need to scroll it up a little bit. Now, if I use my previous theorem about this equivalence of matrices, or of metrics, sorry, I can say that I have the following relation between the metrics. Euclidean metric, obviously it's non-zero, it's a positive definite. It doesn't exceed p metric with this factor. That's something we proved with you on in the previous theorem. And then the p metric itself doesn't exceed Euclidean metric. Remember, Euclidean is a d2 with another factor. Here's another factor, and how, and root. So I use this corollary second part of the theorem on my slide in the previous twice. First here, with the index q here. Remember, in that term, there's a q here. This time q is number 2. That's why it's 1/2. And then p played the role of q again, and that's why we have extra 1 on p. So if you are in a position to write something like this in the assignment, you have to make a proper reference to this equivalence between the dp metrics theorem, twice used in this multiple inequalities. Okay, I keep on. Now I can say, what I can say? Oh, look at this. If my Euclidean metric, or if this sequence goes to 0, by something which you called in the first year sandwich principle, you can say, look at this. My p matrix squeezed between the d metric and the d metric on both sides. And there's a typo here. Yeah, do you see the typo? It's a typo. I'll show you where the typo is. You see? It's just a little bit. You see, originally when I said my sequence, I used n for the index of a sequence and m for the dimension, m for Mary. Well, if in that theorem, which compares the metrics, the equivalence theorem, the n factor there, which was there, it was the dimension. It had nothing to do with the index of a sequence. There wasn't any sequences there at all. So that's the typo. This here is supposed to be m, not n. Dimension. If it was n, then we couldn't use the sandwich principle because the factor was growing with the index, but it's not the case. M here is a fixed dimension. We're not altering the dimensions. We're not jumping from space to we're not jumping from space to space. That's how it's supposed to be correctly typed. And now I can use the sandwich principle because my GP number squeezed between the two vanishing sequences with some factors, but the factors are independent. It's just a constant. And that's why I can say that the limit in D of dp sequence is also 0. But now if I use my theorem again, this equivalence in the reverse direction, then this is equivalent to dp limit of a sequence. And here we go. Look at this. I started with the assumption that my xn converges in the Euclidean metric, and I concluded that the xn converges also in the p metric. The key ingredient in the whole argument was this equivalence between this inequality, which allowed me to use the sandwich principle. Yeah, and that's the end of it. I think you can. I don't think I have the opposite direction. So we proved the inequality this way, right? We proved this direction just now. For the opposite direction, you have to. We can use the opposite actually. We can actually use one right straight away, because if you start from this side, then you make a step here. Limit of dp's go to 0. Then your Euclidean metric squeezed between the number 0 and the vanishing sequence. So d numbers also go to 0, and you come back. So actually it's easily reversible, the argument. Any questions? Okay. No questions? No, it's a nice proof, actually. Well, these arguments, these tricks, or these methods which surround metrics, I don't know, I like them, and I hope you like them as well. Trust me, you won't see many opportunities for the proofs in this. I mean, as we go on through this topic, the material will get harder and harder, and from some point, I won't be able to show you such a detailed proofs because you're not on that level to accept those proofs. Whereas these proofs, on one hand, they give you really solid, really beautiful piece of mathematics. On the other hand, they on a level which is accessible to you. And that's why I use this opportunity just to have fun, to put it short. Later on, there will be harder theorems with the harder proofs, and we need to skip them because you're not on that level yet to get to enjoy them 100%. So I'm not going to steal the fun from you. Later on, with the other topics, you will enjoy them 100%. Any questions? I was just saying this just to let other people to copy things if you can still copy. All right, let's just go back to my main sequence. And, well, now we can say, after we just proved this, after we just established that actually the limits with respect to the metrics, G or GP or any other metric, they're actually independent on that metric, we can safely, in our notations, drop this prefix, D dash, and don't use it anymore. Because, as we just saw, there's no difference which metric you use. The limit will always be the same. But we just work hard to see that conclusion. And it's, for instance, if you go to the infinite dimensional spaces, it's no longer true. Oh, well, this is already a simple slide. This is already something we don't have enough. We can't accept. I mean, it's a harder proof. We can't really look into the very much details of that in this topic. It discusses what is called the Cauchy sequences. It's Cauchy sequences. It's the thing which helps us to address this issue I mentioned today. When you test a limit, in a particular numerical example, like in one example we did today, if you test a limit, you need to know the value for the limit. Otherwise, you can't really use a definition. Cauchy sequences address that problem. With Cauchy sequences approach, you can test whether the sequence converging without knowing the limit itself. So the Cauchy sequence is something like this. It's a sequence which satisfies this relation. For every positive epsilon, there is an index n, such that after that index, the elements becomes close to each other with the distance less than epsilon, with the metric less than epsilon. No matter how far you go, no matter how far the difference between m and n. For instance, little n may be close to n, just after capital N. Whereas the m from M may be really far ahead, and still the difference will be just epsilon. If you have such a sequence, we call it Cauchy. And the theorem says sequence is converging if and only if it is Cauchy. We're not going to prove that. Even though probably you will be able to get the proof, but it's rather long, lengthy proof with not much of a fun, I'd say. That's all I have to say in relation to the Cauchy sequences. Yeah, last thing I have to discuss with you, and that will make our study of limits complete in terms of there won't be any logical gaps in that limits. It's a slide which I call limit of sequence by components. It's only 5 minutes left. Oh, that's bad. But it's all right. I mean, like I said, the set of these handouts which I uploaded on the website, they are so huge because I just miscalculated. So we're not going to cover all of it in this week. I'm going to cut them short and move the piece of it over to next week, so we're not late or anything. Right. So what does it say? It says this: if you have a sequence of, again, vectors in m-dimensional space, you see I need to use the m for dimension because n I use as an index of my sequence. It's something, it's a typo. I made one typo about that already. If your sequence be given by components, and on this occasion I have to use double indices for the components. You see I use the lower index for dimension index and upper index in brackets for the sequence index. And if your limiting point has the components like that, the theorem says computing the limit in terms of my metric, the way we define it today, is the same as if you compute it in a component-wise sense. If we prove this theorem, then the definition of the limit I gave you 2 lectures ago, in a per component sense, it becomes just a consequence of this theorem. So that simplistic definition we introduced for the curves to make the study of the curves easier, continuous differentiability, remember, it now becomes not just the thing we did because we're lazy or because we didn't want to go into the deep. Now it becomes complete logical consequence of the proper mathematical definition of a limit. As long as I show you the proof for this. Or as long as you believe me that this is true. Yeah, I have a proof. Do I? Yeah, well, this theorem justifies early definition of limit for curves. Yeah. I do have a proof, and I have 4 minutes. I think it's, let me just check how big is the proof. It's a nice proof, actually. It's really good proof because, I mean, when I say good, I mean it's not like it represents some mathematical challenges and it shows you how you can use metrics in a really beautiful way. Yeah, that's the good way to describe it. Yeah, I don't want to waste such a proof in 3 minutes. I don't want to rush to that proof in 3 minutes. So we will wind up for today. If you don't have any questions, tomorrow we will start from that proof. Please keep remembering it. Thank you very much. Yeah, thank you very much.